Okay, so here we go. My first video lecture in a little while. It seems like a long time, but I think I have all the software working again. So I think we're in for a successful show. I'm going to do it in parts, so if I run into problems with saving, I don't waste a lot of time. All right, so let's get right into it. As written on the title page, the topic for today is our let's see, lines and planes in space. So we kind of got a head start on this the other day when we were talking about the submarine problem. And for those of you who missed the submarine problem, we started out with something like this, where we had some submarine that was kind of like hiding down here. So there was a sub. And we had one ship here. I think that was actually ship B was here, and then ship A was here. And we're given the direction vectors. So we're given some direction vector from, B could hear this sub down here, and A could hear the sub in this direction here. And this is in 3 dimensions, so I believe this was X, I believe this was, nope, that's not right. That wouldn't have been a right-handed coordinate system, which you guys would have caught me on. That was Y, that was X, and this is Z. And the sub was in somewhere negative Z, implying that the surface, the Z equals 0, so it's water surface at Z equals 0. Okay, and then what we did, the way we solved this thing was to say, all right, well, here's A, and that was at 4, 0, 0. And we said there's some vector going this way. And so we didn't know, we knew the direction, but we did not know the distance. So we said that the distance, actually the location of sub relative to ship A was 4, 0, 0 plus some scale factor, which I believe we called A, times some vector. All right. So what did we do? This is really the initial position plus some scaling factor times that vector. So had the scale factor been 0, i.e. it's in this direction but no distance, well, the sub would have been at 4, 0, 0. Had the scaling factor been 1, the direction to the ship would have been simply, this plus this. So the x-coordinate would have been, well, I don't remember exactly what the vector was, but it would have been simply 4, 0, 0 plus each individual, the x, y, and z components of this vector. All right. Well, this is a really good lead-in, and it's really an example of our the way we write a vector equation. Another way to think about it, this is, let's take a look back to, let's say, 8th grade or so. What would an 8th grader do? And we said that y of x, so y is a function of x, equals some initial position plus some direction times this thing here, right? So we're starting, now normally we'd see this as mx plus b, but I'm going to write it as an initial position plus the slope, which is really kind of like a direction, and then how far we're moving. All right, so initial position plus this. So a line in 3D space relative to vectors would be, we're going to say that r of t equals our 0, right, an initial something, plus some parameter t, this is the same t over here, times the vector v. All right, so what does this mean? So r is the position at, well, I'm just going to call it time t. And r sub 0 is initial position, like that. And then v is the direction vector that we're going to kind of scale. Just like we imagined the position relative to ship A as a scaling of this direction vector here, right? We said we can say the same thing here, where we start with an initial position, which in our original case with the subhunting would be 4, 0, 0. And then t was our unknown parameter. Over here we call it A, and v is the direction vector. So this is really the analog of a line in 2D space, an initial value of y, a direction, and then the parameter, where this is the initial position in 3D space, an x, y, and a z, and then how far it's moved. We're scaling the direction vector as t goes on and on. And then we can say that t can go anywhere from negative infinity t to infinity. And that allows us to go, infinitely in each direction, but parallel to this vector v. Okay, now if we were to take this a step further and parameterize it, all right, so over here, remember, we kind of really thought about this problem in terms of x, y, and z. I could say that x of t equals x sub 0 plus the v component, which I will call v1 times t. Right, so if I'm just worried about how the x goes, it goes that way. So then I think of a y of t equals, well, the initial y plus, now which component here do you think will control the y position? Sure, it'll be v2t. And then finally, the z component fits the same kind of shape there, is the initial z position plus v3, which really controls the v direction of our vector, or the z direction of our vector, times this number t. And once again, t varies from negative infinity to t to infinity. Okay, now I'm going to skip over to an example, and I'm going to pause just for a second before we get there. Okay, so I had to pick a good example to do here, and I'm going to start it on the next page. And the example I'm going to do is, I'm just going to pull it straight out of the book. So 12.5, number 6. And the challenge here is to find the parametric equation for the line passing through some point P, which they say is 3, negative 2, 1. And parallel to the line, and here it's kind of a long drawn out thing, x equals 1 plus 2t, y equals 2 minus t, and then z equals 3t. All right, so what's going on here? We've got some point, 3, negative 2, 1. I could try to draw a sketch of that. Yeah, what the heck, I'll try. So if I call this, let's do it the same as the ship problem. We'll do that as y. We'll call this x. We'll call this z. So 3, negative 2, 1. So let's say 1, 2, 3. And we'll go 1, 2 this way, and then up 1 this way. So we've got some point here. So this is our point P. Now we also have some line. 1 plus 2t, 2 minus t, z equals 3t. Okay, so this is the parameterization of some line. But if we look at this, I'm going to underline this in blue. I'm going to underline it in orange, kind of like a caution. So that 1 and that 2, these are really just starting points for this specific line, right? So this here and then this here. Those are just starting points for this specific line. The direction of this line, right, is analogous to the slope in the y equals mx plus b format. So really, the vector that defines the direction of this line is really just kind of like the slopes. So it's, we could say that v equals, what is it? Well, every time t increments by 1, the x increments by 2. Every time t increments by 1, the y decreases by 1. And every time the t increases by 1, the z increases by 3. So the direction for this vector is really 2, negative 1, 3. The 1 and the 2 here, they don't matter at all. They don't affect the direction of the line. They just kind of determine where it starts. So if I've got this point here, P3, negative 2, and 1, and I want that to be my starting point, I'm going to put this in green because this is what we're really interested in. This is the start point we want. All right, so I can write this parameterization, the solution, as, well, what's going to happen? X equals, it's going to start at 3, and then it's going to go in the direction, every time t increases, it's going to go up by 2, plus 2t. What about the y? The y is going to start at, up here, negative 2, and then every time t increments, it's going to reduce by 1. So minus t. And what about z? Well, every time, 3t, so the vector here is 3. Every time t increments, it's going to go 3 in that direction. So z equals, the original point is 1, plus 3t. Now, it's, we really kind of have 3 slopes here, 2, negative 1, and 3, 2, negative 1, and 3, and our starting point is kind of like our intercept, kind of. Here the analog starts to break down. 3, negative 2, and 1. Here's our starting point, 3, negative 2, and 1. All right, and again, I'm going to specify that my t can go from negative infinity all the way to infinity. Now there's a good example in the book, and I encourage you to look at it. This example, let me go back and find it. For just a line segment, if we wanted to limit this to a line segment instead of a line, we'd have to limit t somehow. So that's example 3, which follows closely from example 2. But that's a good example of that. All right. So the next topic we're going to cover will be the distance between a point and a line. All right, so let's look at distance from point to line. Okay. And the way, I think the book does a really good job of this, say we've got some point P here, and that's this point, and we've got some other point, well, let's see, how do they do that? Say we've got some vector going like this, or some line that's you know, a scaled vector, so let's call it just V. And then we've got, oops, I almost flipped my tablet off the desk here. Let me get rearranged. I get so excited I slowly push my tablet off the desk. And let's say I've got another point up here, S. Okay. Now I've got a couple different vectors here. I've got this vector V. I also have a vector here that goes from P to S. What's a good name for that vector? Well, that becomes PS, that vector there. Well, the distance from PS, or from point S to this, is really the shortest distance would be the perpendicular here. So I can draw that down here as most perpendicular dotted line as I can. And so this distance, we'll call that D. D equals, well, it's magnitude of PS, right? Which is this distance, times, and if we draw theta in here, what is it going to be? The sine of theta. Now, if we only knew the sine of theta, you know, we'd have something to work with. But we recall that the cross product has to do something with the sine of theta. So let's revisit what the cross product is. We know that, let's do a sidebar here. Sidebar / review. Okay, so we know that U cross V equals the magnitude of U times the magnitude of V times the sine of theta. Well, that means that the cross product of these two, PS times V, right? So let's do PS cross V would equal the magnitude of PS times the magnitude of V times sine theta. Well, this is kind of slick because what I'm really after is PS times the sine of theta. I just don't want the magnitude of V. So I could find the distance that I want really equals PS crossed with V divided by the magnitude of V, because that's the only part that I don't want. I don't want the V, so I'll just divide this by the magnitude of V. Now I've got a little problem here, in that the PS cross V actually gives me some vector, doesn't it? I don't want some vector, I just want a simple distance. So I'm going to take the magnitude of this. And what does this really equal? This really equals the PS cross V as PSV sine theta. So this is PSV sine theta. This is PS V sine theta over V, right? And then I can get out the all-powerful, I haven't used this in a while, red pen of cancellation, and my V's here cancel out. So I'm left with exactly what I want, PS sine theta. So PS sine theta gives me this distance between any point in space and the line. And I think this is pretty much plug and chug. So I'm gonna skip the example for this one for the sake of time, and we can maybe do an example in class tomorrow. So I'm gonna pause for a second, figure out what the next topic we have to cover is. Okay, the next topic that we're going to talk about is the equation of a plane in space. Now, I kind of hinted at this one back in 12.1. Let me say equation of a plane in space. And I said that if we have something like ax plus by plus cz equals d, right? What shape does this make? And we kind of take the kind of the intercept approach. So like we set, y and z equal to 0. What is x going to be? We set y and x and y equal to 0. What is z going to be? And finally we set y and z equal to 0. What will x be? And so we can find all the intercepts like this, right? And then those 3 points on those 3 axes will give me the equation of some line. Okay, but there's another way we can do this, and that would be if we had, remember we talked about, when we were talking about the cross product, that a plane can be defined by normal vector, by a normal vector, right? Now the normal vector really just gives us the, so the n vector, or if it's a unit vector, gives us the tilt, and then some point, so p sub 0 gives us the specific location. So I could write the equation of a plane well, what do I know to be true? That from p0, if n is normal, from p0 to p, so any random point, so p is some random point. That's, you guys are going to get confused when you see those notes. P is some, let's call it arbitrary in the plane, and p0 is our defining point, okay? Then that means the vector p0 to p, so we're starting from our defining point, we're going out to p, any point p, must be perpendicular to our unit vector, or our direction vector n, our normal vector n. Now, if it's perpendicular, what has to be true? So perpendicular implies dot product is, what is that? Okay, so when, remember the dot product is kind of the projection of one vector onto the other. So if the projection between two perpendicular vectors would have to be 0. So we could write that n dotted with P0 to P has to equal 0, right? So the dot product between the normal vector and a line that lies on that plane, they have to be perpendicular, therefore the dot product must be 0. So let's define our n vector as, let's just call it, how about just ABC, I think is what the book does. Yeah. A, B, C, or we could call this AI plus BJ plus CK. So then the dot product of that with this P, right? So if P0 is x0, y0, and z0, and then P is just x, y, z, then the vector P0 to P is going to be, or this is the tip, this is the tail, so it's going to be x minus x0, y minus y0, and z minus z0. Okay, so now the dot product becomes pretty easy, right? It's just the scalar product of each of the individual components. So n dotted with P0, P has got to equal A times x minus x0 plus B times y minus y0 plus C times z minus z0. And that has to equal, what does that have to equal? The dot product between two perpendicular lines? That's got to be 0. So we could write this out a little bit more. We could say that ax plus by plus cz equals ax0 plus by0 plus cz0. So if we look back to our original thing here, D, right, D really is kind of how far in or out on the coordinate axes our intercepts are. So let me draw that in here. Where's my pen? So this thing really is, this is D. So if I drew this in, I'll try to fit it on this page here. So if I draw this coordinate system like this, and if I just found my intercepts, right, would be, and I called this, how did I do it before? I think I called this y, and I called this x, and I called this z. My intercept, my x-intercept, for instance, would be, well, it's where y and z are 0, right? Y and z are both 0. So it'd be d over a. And my y-intercept would be d over b. And my z-intercept would be d over c. So d, you know, the bigger d is, the farther this kind of these three intercepts come from the origin. So really d from this definition over here really defines where kind of where my initial point is. Just like over here, d is defined by, lo and behold, kind of the tilt, which is a, b, and c, and where my initial point is, a, b, and c. Okay, so I got to finish this up here. This is really D. Okay, so I can hear Wally crying downstairs, so I got to run down and check on him. I think I might just post this video now because what do we have left to do? The distance from a point to a plane, blah, 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 and then we can start the homework. I think this is a good start. We're going to call this part A of the video, and I'll get part B up tonight. All right, here we go.